Hi you guys, welcome back to my channel. Today we're going to be talking about roots and rational equations and how they relate to exponents. If you find this video helpful, please give it a like and don't forget to subscribe to my channel for more math and science help. So, in my last video we talked about exponents, which an exponent is just telling us how to multiply a number by itself. So if I have 2 to the power of 2, that's telling us to multiply the base, which is 2, by itself 2 times. So we would multiply 2 by 2, and that would give us an answer of 4. A root is the opposite of an exponent. They're inverses to each other. So we're going to work with square roots mainly today. So let's talk about the square root of 4. So a square root is the same thing as a 2 root. And basically what we're trying to do is find what number times itself will equal 4. So the easiest way to do this is we're going to make a factor tree of the number inside of the square root. So to make a factor tree, you're going to start and try and divide the number by the smallest prime number, which is 2. So 4 is divisible by 2, and it's divisible by 2 times. So now we can't simplify this tree anymore because we have 2 prime numbers, so I'm going to rewrite my square root as 2 times 2. Now since a square root is also a second root, that means we're trying to find basically pairs of numbers that multiply. So here we have a pair of 2's, which means we can take a 2 out of the square root. And once we take a 2 out, there's nothing left inside, so our answer here is just 2. Do you notice how a square root of 4 basically reverses the work we did by squaring 4? That's because square roots and exponents are inverses of each other. So anything that you square, when you take the square root, it will revert it back to its original form. So let's talk about perfect squares and how they fit into square roots a little bit more. So we know that some of the most common perfect squares we're going to use are 2 squared, which is 4, 3 squared, 3 squared, which is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, and 12 squared is 144. So if you take any of these numbers that we just squared and you take the square root of them, the square root of 4, it's going to give you the base of your original term. So square root of 4 is 2, square root of 9 is 3, square root of 16 is 4, square root of 25 is 5, square root of 36 is 6, square root of 49 is 7, square root of 64 is 8, square root of 9, or square root of 81 is 9, square root of 100 is 10, square root of 121 is 11, and the square root of 144 is 12. So these are some of the most common square roots that you will see in your algebra class. However, we don't always get numbers that are going to make even positive rational numbers like these, do we? A lot of the time, most of the numbers we take a square root of are going to give us an irrational number, or a number with a repeating decimal. So let's talk about how we would solve those problems. Let's say I gave you the square root of 120, and I want you to tell me what we can reduce this into. So like we talked about when we took the square root of 4, we're going to make a factor tree for this. So you're going to start by dividing 120 by the smallest prime number, which is 2. And then 2 times what equals 120? Well, 2 times 60 equals 120. We're going to do the same thing now with 60. 60 is also divisible by 2, so it'll turn into 2 and 30. 30 is divisible by 2, so that'll turn into 2 and 15. 15, however, is not divisible by 2. So we go to the next smallest prime number, which is 3. 15 is divisible by 3, and that gives us 3 and 5. So now what we're going to do is we're going to circle all of our branch ends. So branch ends are areas that we have fully simplified out of the number 120, right? So that means we're going to circle all of these, and I'm going to put them all back underneath the square root. I'm going to have 2 times 2 times 2 times 3 times 5. So a square root is a root that's looking for pairs. So what you would do next is circle all of your pairs. So we have one pair of 2's, and that's all we have. So because we circled one pair, that means we can take a 2 out of the square root. And the 2 times 3 times 5 will remain inside. When you simplify that, you get 2 times 3 is 6, times 5 is 30. So 2 times the square root of 30. And that would be how you would simplify the square root of 120. Let's try another one. Let's try and simplify the square root of 68. So I'm going to start by dividing by the smallest prime number, which is 2. 68 divided by 2 is 34. So 34 is a number that's able to be divided by 2 again, and that becomes 2 and 17. Now 17 is a prime number, so that means we're done. So we're going to circle our branch points, and we're going to put underneath our square root 2 times 2 times 17. We have one pair of 2's, which means I can take a 2 out and leave the 17 inside of the square root. And this is our final answer. Let's try one where we're not able to divide it by 2 right away. We're going to have to start with another number instead of 2. So let's do the square root of 99. So 99 is an odd number, right? Which means if it's an odd number, it's not divisible by 2. All even numbers are divisible by 2, and all odd numbers are not divisible by 2. So we're going to start by dividing by the next smallest prime number. So the next smallest prime number after 2 is 3. Make our factor tree, and 99 divided by 3 is 33. 33 is also divisible by 3, and divided by 3, that's going to give us 11. 11 is a prime number, so we're going to stop. We're going to circle our branch points, and we're going to rewrite them all underneath the square root, like this. We're going to circle our pair. So 3 times 3 is our pair, which means we can take out a 3, and we can leave the 11 in the square root. So the reason why I like to circle pairs and take that out of the square root is because 3 times 3 is the same thing as 9, correct? And we talked earlier about perfect squares, and when you take the square root of a perfect square, it's the same thing as the base of your exponent. So would you agree that 3 times 3 is the same thing as 3 squared equals 9? Therefore, 9 is a perfect square, and when you take the square root of it, you get 3, which is the logic behind why you can circle a pair, because when you multiply a number by itself, you're squaring it, and take out the base. Let's do a couple practice problems. Let's try the square root of 12. Pause the video and come back when you're done. So we're going to start by creating a factor tree for 12, and we're going to divide it by the smallest prime number. The smallest prime number is 2, and 12 divided by 2 is 6. So now we're going to reduce 6, which is 2 and 3. I'm going to circle all of our branch endings and rewrite that underneath the square root. 2 times 2 times 3. We're going to circle our pair, which means we can take a 2 out and leave a 3 inside. So that's what 12, the square root of 12 would be. It's 2 to the square root of 3. Let's try another one. Let's try square root of 18. Pause the video and come back when you're done. So to simplify 18, we're going to make our factor tree, divide by 2, and you get 9. Now 9 is no longer divisible by 2, so we go to the next smallest prime number, which is 3, and this reduces into 3 and 3, and that's fully reduced. So now I'm going to circle the branch ends and put those underneath the square root. So 2 times 3 times 3. I'm going to circle my 3's, which means I can take out a 3 and leave the 2 inside. And that's your answer. So how would this work if we're not dealing with actual numbers and instead we're dealing with variables? Well, it'll actually work the same way. So let's say I have the square root of x squared. The square root of x squared is the same thing as the square root of x times x. I can circle my pair, which tells me that an x is going to come out and we have nothing left inside the square root. The other thing you can do is divide the exponent, so 2 by 2, and that tells you what the exponent will be on the number you take out. For example, if I have the square root of x to the 6th, if I divide 6 by 2, that tells me I'm going to take out an x to the 3rd, which we can prove by if I draw out all of my x's in that square root, and I circle my pairs, 1, 2, 3, I'm taking out an x times x times x, which equals x to the 3rd. Let's do some practice with these. If I have the square root of x to the power of 12, what would that reduce to? Pause the video and come back when you're done. So, to do this, we're just going to divide 12 by 2, and that's going to give us x to the 6th power. What if I had the square root of x to the 9th? How would I do that? Well, I would divide 9 by 2, and I would get 4. So So that means x to the fourth is coming out, but it's 4 with a remainder of 1, right? Which means we have 1x that we didn't take out. So we have x to the fourth on the outside and 1x on the inside. Let's try that again, but with x to the 13th. X to the 13th divided by 2 is going to be 6 with a remainder of 1. So we take out an x to the 6th, and we leave an x inside of the square root. What if I want to multiply two square roots by each other? What if I have square root of 2 times the square root of 3? Well, here the roots are the same, right? They're both square roots. So because the roots are the same, I can just multiply what's inside. So this is going to become the square root of 2 times 3, which is just the square root of 6. Let's do some more practice with this. What if I had the square root of 5 times the square root of 5? So here, that would just be the same thing as the square root of 5 times 5, which is the square root of 25. But we know that 25 is a perfect square, so square root of 25 is going to be 5. Let's try the square root of 6 times the square root of 3. So that would be the square root of 6 times 3, which is the same thing as the square root of 18. We can reduce the square root of 18. That's going to reduce into 2 and 9, and then 3 and 3. We have one pair here in our 2 times 3, which means we're going to take out a 3 and leave a 2 inside. So the square root of 18 is 3 times the square root of 2. What if I want to add or subtract square roots? In order to add or subtract a square root, you have to have the same root, so both of them have to be square roots, and they have to have the same value inside of the root. For example, if I had 2 square root of 3 plus 4 square root of 3, I can add these together because they're both square roots and they both have the same thing on the inside. In order to add these together, you would just add 2 plus 4, and that would give you 6 square root of 3. But if I had 2 to the square root of 3 plus 4 to the square root of 2, I cannot add these together because what I have inside of my square roots is different, which means they cannot be added together. Let's do some practice with this. Can I add these together? No, I cannot, because what I have inside of the roots is 2 different numbers, so I can't add these together. What about 5 square root of 10 plus 5 times the square root of 10? These two I can add together because they have the same thing inside the root. So that would be 10 square root of 10. Now let's talk about dividing square roots. So if I had 16, square root of 16 over the square root of 4, what I would do is here, I can apply that square root to the entire thing. So that would become 16 over 4, which is going to reduce to the square root of 16 divided by 4 is 4, which is 4, which is 2. Another way I could have done this is 16 and 4 are both perfect squares. The square root of 16 is 4, and the square root of 4 is 2. So 4 divided by 2 is also 2. So this proves that this method works. Let's try some more problems like this. Say I have the square root of 100 divided by the square root of 10. Let's simplify this problem. So I'm going to start by bringing the square root up and over the whole thing. So we have 100 divided by 10 all in the square root. Now we know that 100 divided by 10 is 10. So this is simply going to be square root of 10. Let's try another one. Let's try the square root of 12 divided by the square root of 4. So I can simplify this into being big square root 12 over 4, which is going to reduce to be the square root of 3. What I also could have done is I could have reduced 12 and 4 separately. So the square root of 12 would reduce into 2 root 3, and square root of 4 would reduce into 2. Those 2's would cancel out, and then we'd be left with the square root of 3. This has been solving square root problems. If you found this video helpful, please give it a like and subscribe to my channel. Thank you. Have a good day.